Okay, in this video we're going to start taking a look at graphing transformations of secant and cosecant. So I've got this problem up on the board. I want to graph y equals 3 secant of x over 4. Okay, so anytime I'm doing a transformation of secant or cosecant, I'm basically going to do it as a two-step process. I'm going to graph the corresponding transformation of cosine for secant, because of course secant is the reciprocal of cosine, or of sine if I'm doing a cosecant one. So in this case, the corresponding transformation would be y equals 3 times secant of x over 4. So doing the same thing, y equals 3 times cosine of x over 4, okay? So keeping the multiplying by 3 and dividing by 4 exactly the same, but replacing secant with cosine. And then once I've done that, I will flip the bumps, just like we did in graphing our basic secant and cosecant graphs. So what I want to do is just do these two steps for this particular problem. Once we've done it, we'll take a look at exactly why it is that this works. Okay, so let me clear some space. I want to graph, even though that's what I ultimately want to graph, I'm going to start with y equals 3 cosine of x over 4. Now I'll draw that as a dotted curve, because again, that's just my helper graph. So I want to remember that anything I'm doing to x before I plug it into cosine, that's going to affect things horizontally. And anything I do after I evaluate cosine is going to affect things vertically. Now for the vertical, I know that usually cosine, just a basic cosine graph, would have a high value of 1, a middle value of 0, and a low value of -1. Multiplying by 3 just stretches all of that by a factor of 3. So I'm now going to have a high value of 3, a middle value still of 0, and a low value of -3. Now obviously I'm using a different scale on this vertical line than I am on this line, because I've got limited space here, so I didn't want to actually make it 3 times as tall. But I'm just using this not to actually compare the scale of things, but to indicate what my new high, middle, and low values were. Okay. Now for the horizontal transformations, we want to remember that cosine would go through one complete cycle as the input varies between 0 and 2 pi. I'm going to probably want to adjust this because cosine at 0 is not 1. So when I'm ready to flip the bumps, that's not going to correspond to an asymptote. But I'm going to go ahead and just get this, and then once I've got this, I should be able to extend as needed to get so that I can start with and end with an asymptote. So to solve for x, I would just multiply through by 4, and that's going to mean that x varies between 0 and 8 pi. Okay. So now I can say that my new period should be 8 pi minus 0, my new ending point minus my new starting point, which is just 8 pi. I can confirm that that's the case because that should be 2 pi, the original period, divided by, be careful, not divided by 4, but divided by 1/4. I divide by the number that I'm multiplying by x, and dividing by 4 is the same as multiplying by 1/4. So that would be 2 pi times 4 over 1. That would be 8 pi. Excellent. So that works out. That's my new period. And that means that the new increment is 1/4 of that, which would just be 2 pi. Okay. Remember, the increment is just taking that period and dividing it up into 4 pieces. Those would, for the original graph, those correspond to the 4 quadrants. Now they correspond to where those 4 quadrants get translated to. So that basically means that on my x-axis, I can start at 0. I'm going to count over by 2 pi until I hit 8 pi, which is my ending point. And I think for this, I didn't say this at the beginning, let's just sketch one full period of this. Okay. So if I have 0, then I would go 2 pi, 4 pi, 6 pi, 8 pi. Now my new high is going to be at 3, and my new low is at -3, and cosine starts at a high value. So I'm going to connect the dots with a dotted curve, because this is just my helper graph. And then I realize that if I'm going to flip the bumps, I don't actually want to start here. I want to start and end at an asymptote. So I have two options. I could extend this to the next place where cosine would be 0, and I can see that would be -2 pi. I think I'm going to do that. Okay. That means if I'm starting here, I want to end here, because I just want one full period. My other option would be that I could start here. In that case, I want to extend the graph over here to 10 pi. So I could either go from 2 pi to 10 pi, or from -2 pi to 6 pi. I kind of prefer this because I like to include the y-axis when I can. Okay. All right. So I'm going to actually just erase that so I'm not tempted to keep going. If I were actually drawing cosine and that was my goal, I would of course have arrows attached to indicate that it keeps going. When it's just my helper curve, it's okay to just draw the number of periods that I need. So now I can draw in my asymptotes, which occur wherever this cosine graph is equal to 0. And then I can flip the bumps. So we're getting something that looks like this. The same basic idea. We've got these alternating U-shaped curves, but the location of the asymptotes has moved, and the high and the low points have changed. Okay. Now, why does it work to transform cosine first and then secant? Well, I can see that the period of secant is still just 2 pi. So if I were going to solve for the x values that were important to me, I'd do exactly the same work that I did for secant. So I'd find exactly these same x values. Okay. What's a little bit more interesting is taking a look at this vertical change, because now when I'm flipping the bumps, it no longer actually corresponds to taking the reciprocal of what I've graphed, because the reciprocal of 3 is not 3. The reciprocal of 3 would be 1/3. So I'm not taking the reciprocal of this. But if I think about what's happening, the original graph of secant had a low value of 1. If I'm multiplying by 3, that's going to bump that up to a low value that's 3 times as big, so it's going to bump it up to 3. So this process of flipping the bumps is no longer corresponds to the algebraic task of taking the reciprocal, but it's kind of neat that transforming the cosine graph gives me something where the high point of this cosine helper graph is in the right place for the low point of the secant graph that I want to graph. Okay, so that's our first transformation. I'm going to put another one up here. Here I reviewed what happens when we multiply by numbers. In this next one, we're going to review what happens when we add or subtract numbers to things. So I'm going to take a look at y equals 2 plus 3 times cosecant of x minus pi over 3. Okay. If you're feeling confident about remembering how these translations work, these basically just shift things up and down and left and right. If that's the case, go ahead and before you watch the next video, try it on your own and then turn on the next video to check your work. If you're not feeling confident, you feel like you need some review, watch the next video, and then at the end of that, I'll give you another problem to try, and for that one, I would suggest that you try it on your own before watching the next video.